Well, yeah, but that when I thought it was just that I messed up something and said it.
All right. So we left off last class. I believe we finished up kind of talking about weighted variances, weighted means. We did some stuff with the midpoints, right? We looked at a couple examples where we had to use midpoints instead. The next thing we're going to talk about is percentiles. So first of all, for the Connect homework, after today, we should have covered everything you need to answer every single question. So if you were trying to work through the last few questions there, you probably saw some things that we haven't went over yet, right? So today will be kind of the last stuff that you'll need to answer all the questions on that. Excel, you should have everything you need. I might show you something at the end of class that might help you a little bit in Excel and just kind of moving forward something that will be helpful. So percentiles, did someone here ask me about percentiles at one point? Or is it a different, one of my other sections? But, if you've taken the SAT or hopefully some of you take like the GRE or, trying to get maybe to grad school, they always tell you what percentile your test score is in, like, which is sometimes cool to see, other times depressing. Right? But, all it means is that if I'm in the 90th percentile, so P here, we're just choosing a number. So the 90th percentile, it means my score was better than 90% of the other scores, right? So I'm in the 90th percentile. That means that 90% of the other scores were below mine, which also means that 100 minus P, right? So 100 minus 90 would be 10, right? In the 90th percentile, my score was lower than 10% of the scores, right? So higher than 90% of the scores, lower than 10% of the scores. That's all the idea of a percentile means. Like I said, I think most of you are probably like it's pretty common terminology. You've seen it used before. I always love the when you're a kid and you go to the doctor, I don't think you don't have one. I used to see this chart, right? And this is like one of the most complicated charts ever. I don't understand why they don't put it on several charts, but you can find how old you are, and then based off of your height, which one of these percentiles that you're in. I think they've got weight here. No, this is centimeters. Yeah, so this is just the height one. You can figure out where you're at. I think when I was 15, I was like 5 foot. So that's like what, 60 inches? So I'm like below the percentile or something when I was 15. So, I mean, you can play around with this and figure these things out. But this is the idea of how did they get these values for these percentiles, right? So how do you come up with the values for these different percentiles? It's based off of some data that you're looking at, right? So we're going to use really small data sets. Obviously, in practice, they would be much larger data sets, but this gets the idea kind of across. So let's say we've got a bunch of observations. What we'll do is we'll arrange them from smallest to largest, right? So think about it if I had 100 observations, it'd be pretty easy to think about, and I arrange them from smallest to largest. Well, the 90th percentile would just be whichever value is in that 90th position, right? Because it would be greater than 90% of the values, but less than 10% of the values, right? So it's easier to think about with that, but if we have different sample sizes, n, we can find the position that any percentile is in by using this formula. So we just plug in the percentile we want, the 25th, the 30th, the 90th. We plug in the number of observations in our data set, and this will tell us the position that has whatever percentile we're interested in. Okay? So if it's an integer, we lucked out, because if I have a data set and I plug everything in, and let's say I want the 80th percentile, and I get that is in the, 21st position of my data set, right? After they're arranged from smallest to largest. Well, then I just go to the 21st position and see, okay, what value is in that position. The problem is, what if it's not an integer, right? So if it's not an integer, I have to do something that's called interpolation, right? If I get that the 90th percentile is in the 34.3rd spot, well, there's no 34.3rd spot, right? There's a 34th number and there's a 35th number. But what that is telling me is that the value that would give me the 90th percentile is somewhere in between the two values in those positions, right? So what did I already say? I already forgot. 32.3. So the value would be somewhere in between the values in the 32nd and the 33rd position. Okay. So that's what that formula does for us. The way we do this interpolation is I'll explain it, I think, the most useful way, and then maybe some other ways that I don't think connect this easily. But let's say I've got these different funds, right? And kind of what their value is. So kind of think about this like that. How much they're returning or the change in their pricing was. So we've got the data arranged from smallest all the way to largest, right? And I think, the only trick here is sometimes to remember like negative values, right? Larger negative values are going to be all the way to the left. So if I want the 25th percentile, I'm going to plug in that 25 for P. That's the percentile I'm interested in. My number of observations, right, is 10. So I plug those two values in, and I get that the 25th percentile should be somewhere in between the second and the third position, right? 2.75. Okay. So what I know is the 25th percentile value is somewhere in between -7 and 8. I'm rounding those numbers there, but right in between those values in the second and third position. So I don't want to simply take the average of those two because this is telling me it's in the 2.75th position, which means that I'm actually a little bit closer to the value in the third position than I am to the value in the second. So what I'll do is I'll look at this formula, whatever decimal is associated with it. So here, 0.75. I'll use that as one of my weights. And then my other weight is just going to be what would get me up to 1, right? What would complete the entire proportion, right? So 0.75 and 0.25, right? If this was 0.3, 2.3, I would use 0.3 and 0.7. If it was 2.9, I'd use 0.9 and 0.1. So that's how I identify the two weights, but then I have to think a little bit and say, okay, which position am I closer to? Here I'm a little bit closer to the third position. So I'm going to weight that value with the higher weight, right? So the 0.75, I'll multiply that by what? 8.09, the value in the third position. And then the value in the second position, right, is the one that I'll weight by the lower weight. Right? So multiply that by -7.34. So the idea with interpolation is just that I don't want to simply take the average because I know I should be a little bit closer to the third position, which means that the value I should be finding should be a little bit closer to 8. So if I do this formula and I get something, it should, if I'm thinking about in between -7 and 8, but I'm quite a bit closer to 8, I'm guessing it's going to be like 3, 4, 5, somewhere around there. Let's see. Yeah, sure enough, it ends up being 4.23. Right? So the idea is that I'm in between two numbers, but I know that I'm not exactly in the middle between these two numbers. And so I need to weight the one that I'm closer to a little bit higher. Okay. Any questions on that? What if I had asked you for the 33rd percentile? So what will we do here? We would plug in into that equation, 33 over 100, right? I can't do this math. So what does that end up doing? 11 third. I think I chose this number.
3.63.
What is it?
3.63.
Awesome, thank you.
I think I did my other.
3.63. Sounds right. Okay, so I don't want to use that then. Hold on. I chose this wrong. I think what I want. Let's try to do the 25th. That would give me what, 1/4 of 11? Or sorry, that's what I did. No, I don't. I need to go the other direction, don't I? If I do 40. What do I get if I do 40? So I get 11, so 44 over 100, or no, 4. Right? That's what I want to do. Okay. So the reason why, you'll see why in a second why I had one to choose this number. So now I want the value that's in the 4.4th position, right? So what are my weights going to be here? 40, 60. Yeah, or to actually simplify, 0.4, 0.6, right? But what position am I closer to? The 4th position, right? So the value in the 4th position is actually the one that I'm going to weight by the heavier weight, right? Kind of see how it's flipped from the one we were doing before, because the one before, whatever the decimal was, we were already closer to that value. When you start with when you have a decimal that's below 0.5, it's a little bit more counterintuitive, but that's why I think writing down what your weights are and then what value gets weighted the most, it's an easier way to think about it no matter what that decimal is.
How are you closer to the 4th if you haven't passed the 3rd?
How am I closer? Oh, so this is 4.4, right?
Yeah.
So it's telling me the 40th percentile is in the 4.4th position.
Oh,
so,
position.
Yep, position. Okay. So I know that I'm in between the values in the 4th and 5th position. Yep. So that heavier weight, I'm going to multiply by the value that I'm in the position I'm closest to, which is the value in the 4th position. So 0.6 times what? 18.33. I'm going to add to that the second weight of 0.4 times the position I'm a little bit further from, which is the 5th position. So multiply that by 33.35. Okay. I don't know what this ends. I can't do this math in my head. I'm not even at the 10. So, but this is the same, this setup, and this is, I wanted to show you an example where you had a decimal that was below 0.5, and that's why the process of writing out the two weights and then determining it, I think, makes a little bit more sense. What if I end up with so if I end up with an integer, it's easy because it's just whatever value's in that position. But what if I end up with like 7.5? I don't know what percentile that would be, but let's say the position of some percentile I'm interested in is 7.5. Why would that be pretty easy? Just the average, right? My two weights would be 0.5 and 0.5. It's the same as just adding up divided by 2. All right. So we're okay with kind of that idea. So let's say now that I kind of come up with some of these percentiles, I'm feeling a little bit more comfortable with it. What can I do with these? Like, I guess they're interesting, but they actually have a wider use. So the first, second, and third quartile, we're going to call, or sorry, the 25th and 75th percentile we'll call the first and the third quartile. The 50th percentile is actually going to just be the median. Right? Think about it. It's the 50th percentile. It's greater than 50% of the observations, less than 50% of the observations. That was the definition of the median. So we've got these different kind of quartiles and then the median. We're going to graph these out. And I think, like, I don't know if you guys haven't seen it in any classes. I don't know, like box and whisker plots. You ever seen those before? So this is basically how you make them, right? And they don't come from nowhere, right? You start with some original data set, you arrange it from smallest to largest, you calculate these percentiles, the 75th, 50th, and 75th, and then you use those to calculate some other things, right? So let's first focus on those quartiles. So what I would do is think about, let's say I come up with that first quartile and the third quartile, and then wherever that second quartile is, I draw a line kind of in the middle of that box, right? And so I don't know, maybe this is like 40, 30, 60 or something like that. So basically you're using your y-axis to kind of plot these values, but the first and third, you kind of draw this big box with. Then your median, or that second quartile, you draw a line, in that box wherever that value happens to fall. And I'm not going to make you do like a lot of this by hand. I'm only mentioning this because I know that other courses might use it. And also there's something, and you can there's like a default in Excel. I don't have you guys ever use it, but maybe we'll take a look at it if we got some extra time next week. That'll plot these for you. So you've got your third, your first, and your second quartile. You then come up with this, I call it the IQR here. It's your inner quartile range, right? So if it's the inner quartile range, all it is the difference between your third and your first quartile. So here, right, my interquartile range would be what? Yeah. I then am going to use that to come up with my lower and my upper limit. So here I'll take my third quartile. So my value is 60. We'll go Q3 plus the interquartile range is what? 60 plus 30. So we're going to then draw this kind of line up to whatever that upper limit value was. For us, it happened to be 90. And then kind of draw a little like this. Actually, I forgot something. It's not 90 because I have to multiply this by 1.5. So 30 times 1.5 is 45. And then that's, we get what, 105? So that sets my upper limit, right? Then to get my lower limit, right, I'm going to take my first quartile minus 1.5 times that interquartile range, which is 30 minus 1.5 times 30. So I get what? Negative 15. And that's going to be my lower limit. Okay. So that's how I create my box and whisker plot. Basically, I have to calculate 3 percentiles. Then using those percentiles, I can come up with the rest of the stuff. So what this does for me is it says, look, this lower and upper limit based off the data, if I see anything outside of this range, it's what we're going to call an outlier, right? It is an extremely low or high value that I shouldn't be seeing. Okay? So this is called the Q test, right? So if I had an observation that was like 120, I could, by the Q test, identify that as an outlier, and I would then be justified in excluding that observation in some of my analysis, right? Because it's so extreme that if I calculate things like the mean, it's really going to influence it. And so this is like, if it falls outside that upper and lower limit, I don't have to use it. And also, I thought that was a great meme. So, right, please don't reject me as an outlier. I thought it was fun. But yeah, you'll see these used a lot in class for a lot of different. I think marketing likes them. I don't know why, but they're a good, kind of way to get rid of these outliers, these problem points in the data set sometimes. So the next thing, is there any questions on that? Yeah.
Is there a preference between horizontal and vertical?
For drawing those? No, I don't care. I think it's probably easier to draw them vertical only because, like, I don't know. That's how I would think about plotting things, like, because it shows that higher values are above the other ones, but it doesn't really matter. Other questions? Actually, I wasn't like stalking that like the question was bad. It's just like because I know that there are people who I know there would be people. Yeah, that's what I scoffed, because I know there would be people like, you should only do on this. It doesn't matter. Like they're lying to you. It doesn't matter. It's just a different axis of looking at the same thing. So the next thing we're going to talk about is the relationship between two variables. So up to this point, we did a little bit with scatter plots, but for the most part, like we don't have any measure of the relationship between two variables. So we'll talk about ones today. Yeah, we should have plenty of time. And if one variable increases, does the other variable go up, go down, or not change? Right? We're interested in it. No matter what it does, it's interesting. I just had I'm helping someone with their honors thesis, and we were talking about like narrowing down their question. And we're like, well, what if I do this? Like, if I don't find anything that's not interesting, I was like, well, no. Even if you have a question, like if X changes and Y goes up, down, or does nothing, any of those are interesting. Even if it doesn't change, that's interesting, right? It's telling you that there's no relationship here. So, we have two simple measures of this, the covariance and the correlation coefficient, or just kind of referred to in general, a correlation. Right? So to come up with that correlation, we actually first need to find the covariance. Okay? So we'll talk about the covariance first, which is, let's assume we have two variables, X and Y. Right? We're just going to keep this in a general form. These could be any two things: income and education, age and I don't know, age and the amount of wealth you have or something, but any two variables we're interested in the relationship between. So the formula is going to look something like this. But if we remember what we know about the variance, this isn't too tough. Okay? So if we have a data set, and we have all these observations, but we have two variables, x and y now that we're interested in. We'll first calculate the mean of the x and the mean of the y variable. We will then look at every single observation's deviation of their x value from that average x value, and multiply that by that observation's deviation, or sorry, that observation's y value's deviation from the average y. Once we do that for every observation, we'll add them all up. And then kind of just like the variance, we weight all of them equally. So just we divide by the total number of observations here. Or kind of like multiply each one by 1 over n. This is an easy way to think about it. Sample covariance, the exact same process, but just like the variance, we now divide by n minus 1 instead of n. Right? So pretty similar. We're not squaring anything, and we'll see why in a second. I have an example that I think helps make clear why we're doing what we're doing in that numerator, but it's a little bit easier to see with some actual values. So here's our two formulas. So what is the covariance actually telling me? Well, if I go through all these observations, add them all up, and I end up with a positive value, it's telling me that there's a positive relationship with x and y. As x goes up, y tends to go up as well. If it's negative, it's telling me that as x goes up, y tends to go down. And if it's 0, there's really no relationship between the two things. X can go up or down, and y really doesn't change. So before we get to the numbers, I'll try to give a little bit of an insight as to what this formula is capturing. Okay? So notice, anytime I'm looking at an observation, and let's say we're doing years of education and income. So X is years of education, Y is income. Anytime I have an X value or years of education that's above the mean, right, then this is going to be a positive value. Okay? If I have then also income that's above the mean income, this would be a positive value as well. That observation was evidence that if my years of education is above average, so is my income, right? Positive times a positive, I have a positive value. If I happen to look at an observation where the person had below average education, this would be negative. And if they also had below average income, the second component would be negative as well. Negative times negative is a positive. So if they're both below the average, right? The same observation, if both values are below the average for different variables, or they're both above the average, I get a positive value added to that covariance numerator. Well, that's because those observations are evidence that when X is on one side of the average, Y tends to be on the same side of the average. All those observations are going to be adding positive values because it's telling me that these two variables tend to be on the same side of the average. Now, anytime I see an observation, let's say that had above average years of education, but below average income, well, now I've got a positive times negative because that observation was evidence that when X is on one side of the average, Y tends to be on the other. Right? So that's really all this is capturing. Now, it's not just capturing if they're on the same side, like the distance from the average is also playing a role. So when we look at, I have a data set like this, so instead of education income, we'll use height and weight. Intuitively, we probably know this covariance is going to be what sign? Positive, right? I mean, as someone is, grows in height, they on average probably tend to be a little bit higher in weight as well. I don't know how strong that correlation is, but I'm sure it's positive if I had to guess. So the way we'll calculate this covariance, we'll go through, I've got average height here and average weight. This was like a pretty large sample, 44,000 people. I think it tended to be a little bit younger, which is why this height might be a little bit lower than you would expect when it's like 5'4", or it might have just been females, I can't remember. But we've got all these different observations and we went with covariance. So we can use these averages, right? We'll go through the first observation. This person is, above average height. So when I take 70.4 and subtract 63.9, I'm gonna get a positive value. But they are below, they're above average weight, right? We looked at their, they're below, sorry. 179 is below 187, right? So they were above average height, right? But they're below average weight. So we're going to get a positive value times a negative value. That is an observation that these two things tend to be on opposite sides of the average. But we then go to the next person, right? They're just barely below average height, but they're quite a bit below the average weight, right? So there we have evidence from that observation that these two things tend to be on the same side of the average, right? And we basically go through every observation. Then when we add them all up and divide by n, it's almost like, well, what was the average relationship between these two variables across every single observation? So, do I have some values in there? Why don't I have those? I know that I have them. Let's see. Did I open the wrong one? That is possible. So skeleton, maybe I had them just for these other ones. Let me check. Maybe I didn't have it. I thought I did. Oh, here it is. Yeah, I thought I had pasted the other. I'll re-upload these because I thought I had this. Looks like I truncated it somehow. There we go. Okay. So these are the other columns that I thought I had up there, but apparently I somehow didn't include them. So notice for this person, right, they were above average height, below average weight. So that was an observation that these two things tend to be on the opposite sides. This one, notice, even though they were both on the same side of the average, the distance from that average also comes into play, right? I'm not just putting a 1 or a 0 for whether it was above or below the average. I'm looking at the distance from the average. So notice, because this person was just barely below the average height, the value that gets added to the numerator is very small, right? Because even though it was an observation that provided evidence that these two things tend to be on the same side of the average, right? It wasn't strong evidence, right? This thing was barely on the other side of the average. And then you go through the other individuals as well. They both were below average height and below average weight. So negative times negative, they were both observations that provided evidence that there's a positive relationship between these two variables. So we would go through and do this for every single observation, add all these up, and then divide by the total number of observations that we have. Or if it's a sample data, which I think this was, we would divide by what? 44,000 minus 1, right? Any questions just over kind of the idea of the covariance, what we're doing here? And if you have the original data in this X and Y variable in columns, doing the work to the side of it like this is probably the easiest way to do it by hand. Any other questions? So if we do this, we get 76.09, which is cool. Now I've got this, so on average, there is a positive relationship between height and weight. That if you're taller, you tend to also be heavier. Right? But how strong is that relationship? Like 76 what? Well, I don't know. Height was measured in inches. Weight was in pounds. So inches times pounds, 76 inch pounds. Like I don't know how to interpret this, right? Like what are the units don't really mean anything. And I don't know if 76 is a high number or a small number, right? And it's going to depend on what two units I have. Inch pounds probably have a wider range than, I don't know, year dollars or something like that, right? If I'm looking at education and income, years and dollars. So we need to do a little bit more work. So the covariance is great, but it's influenced by just how much variation exists in those X and Y variables to begin with. So what we're going to do is we're going to scale this covariance to create the correlation coefficient. And I'll kind of give you an idea of like the math behind why. It won't be like exact proof, but oops. So if I want to get the correlation coefficient for the population, we'll kind of use this Greek letter rho, and then the sample, we'll use kind of just our English alphabet letter R. Okay, so correlation, I guess, is how to remember that. So correlation coefficient, or just the correlation between two variables, we're going to take the covariance, whether or not it's population or sample, and divide it by the standard deviation of each variable. So the reason why this works, or why this scales the correlation, because before I couldn't compare across variables, right? A covariance for inches and pounds, I couldn't compare that to the covariance between education and income. But with a correlation coefficient, I can compare the relationship between any two variables and say which one's stronger, which one's weaker. So if we think about what the covariance was, I'm going to write this out in terms of sample. Right? So that was my covariance. So that's my numerator. I'm then going to divide that by the equation for the variance, sample variance, for each of these variables. And I'll get out of the way here in a second. All I've done there is plug in the equations for my covariance and my standard deviations. And actually, I forgot something. What did I forget? This is the variance. I'm actually dividing by the standard deviation. So I need to take the square root of both of these. So the reason why this scales our correlation is really what this represents is the dispersion that existed in my X variable and the dispersion that existed in my Y variable. So on a conceptual level, I'm trying to use that original variation. And I know that the variation I see in this covariance will depend on what the variation was in the original two variables I was looking at. But you can kind of see what's going to happen here. I mean, I've got like an xi minus an x bar, a yi minus a y bar. I've got an xi minus an x bar squared, but I'm taking the square root, right? So this is not the correct math proof, but it's kind of like, okay, well, these cancel. I'll have the square root of n minus 1 times the square root of n minus 1. That's just n minus 1. So I've got the same denominator on both of these. Now I've got like the sum of the x's times the sum of the y differences, sum of the x times. Like you can kind of see it's very similar components. So it's almost like everything's going to cancel, right? So it's not that everything's going to cancel because, right, this is the sum of the deviation in x times the sum of the deviation of y. And this is just the sum of the deviations multiplied by each other first. So it's going to be a little bit different. But the idea is we can use these standard deviations to account for the original variation so that when we divide that covariance by each of the standard deviations, we actually end up with a statistic that we know is going to be between 1 and -1. So one would be, is there a perfect correlation between these two variables? Right? Is there almost like essentially a 1-to-1 increase in these two variables? Right? -1 would be the most extreme negative, like as x goes up, y goes down by that exact same amount, right? So like a perfect negative relationship. Right? Now, in practice, we're never going to see 1 or -1. Like these are like kind of like we approach them in the limit, right? Like we approach them, so it's in the limit, these are 1 and -1, but in practice, we never actually see those. And then 0 represents no relationship. So basically, anything in the positive range, right, is a positive relationship. Anything in the negative range is negative. We can start to compare things, right? So let's say I had calculated these, and I get the correlation coefficient for, we'll do the height. So we'll do height, weight. And then I have the correlation coefficient between income and education. First of all, I know that I have it here in a second, so we'll grab this real quick. Right, so we have that covariance. I could then go back to the data. Pretty easy, especially in Excel, to quickly calculate the standard deviation of the x variable and the standard deviation of the y variable. And then it's just a matter of plugging these into a pretty simple formula. 76 divided by approximately 4 and 43. I get about 0.54, right? So this covariance between height and weight is about 0.54, which is that a strong relationship? So there's different rules of thumb you can use. Some of the questions, I don't know. Like the pre-built questions that Connect has, some of them are like, oh, is this a strong relationship? Yeah, it's 0.57. Well, I mean, you could draw the line anywhere you want. Probably above 0.5, we would consider to be like pretty good evidence there's like a fairly strong relationship between these two. But I mean, it depends on what you're interested in. If you're worried about, you know, the correlation between things like, you know, taking a vaccine and getting sick, right? You probably don't want that to be at 0.5. You probably want it to be 0.8 or 0.9, right? But, you know, this is a moderate, evidence of a moderately strong positive relationship, right? As we get closer to 0, we get weaker and weaker relationships. So let's say I told you that the relationship between education and income is actually stronger than the correlation between height and weight. Well, then you know that this correlation coefficient would have, and actually I'm writing these wrong. I'm writing these the covariance. Sorry, correlation coefficient. If it's stronger, then you know this has to be something above 0.45. So 0.7, 0.6, right? And then if you tell me, well, the correlation between an exam score and the hour of Netflix watched, right, is a stronger negative relationship than even income and education. So what are some potential values for that correlation?
-0.8.
-0.8, -0.9, right? It basically, you know, it's negative, but it's a stronger relationship than between income and education. It's just that it happens to be inverse as opposed to. So we can start to do like things like that. Once we have the correlation coefficient, we can compare across any two variables. Also think about when we were dividing the covariance, I said I had like inch pounds. Well, then I had inches times pounds on the bottom, so the units always cancel, right? So I get this nice unitless measure that I know is between -1 and 1. Okay? Any questions on that? We keep moving here. So, you know, this kind of relates to what we were talking about with the scatter plot, right? We're really just trying to pick up, essentially, if I drew a line of best fit through there, kind of like what would the slope be? That's one way to think about what the correlation is telling you. I'm not going to waste, I mean, we could do these. It's pretty simple math. I mean, well, actually, there might be multiple answers to this. We'll use the high clickers today to kind of take some points in here. So the first question I'll ask you is, and there might be multiple answers to this, so as long as you choose one of them, it'll be kind of correct. Which of these answers could you rule out for being the correlation coefficient between the height and weight of these children, I guess, 21,000 children? So which of these answers, yeah. Well, I was going to use an I-3 question, but yeah, we'll wait and do it on the next one. So here we go. Don't answer me out loud this time. We're going to use I-clicker here. If you respond already, whatever you hit last will be recorded. So let's say we have a different example, and we've got what, X variable of like someone's looks and a Y variable of their wage. Which of these correlation coefficients, given the information you have above here about the covariance, as well as the two standard deviations, respond with which one you could rule out. And there might be multiple ones, so just choose one of them. I think there's 1, 2, 3, 4, 6. All right, so just respond with one of them that you can rule out for sure. There are 13 of us, right? I got 14. Oh, there we go. Okay, closing it out. Right, which of these should you be able to rule out? Yeah. A. Why can you rule out A? Yeah, it's outside the range of 1 and -1. Which one can you also rule out? D. Yeah, you can also rule out any negative values here because your covariance is positive, right? Your standard deviations are always going to be positive. So the sign of your correlation is going to be the same as the sign of your covariance. Remember, we're just scaling the covariance, right? So we're not changing its sign, we're just changing really its magnitude, right? We're scaling it to be between 1 and -1. So that shouldn't have been too bad. I think what I have here, we'll see how long this clip is. Or if the clip still works. We can kind of end on this going into the weekend.
Yeah, I mean, the thing is, people like Geico because it's just.
Oh, isn't this playing over? How do I change my? Well, I got an idea.